So let's look at two Euclidean things that I use all the time, even when I'm doing non-Euclidean stuff. First is cyclic quadrilaterals. A cyclic quadrilateral has its vertices on a circle. And there's a property that goes with this. When you have the start, like right now, that's an inscribed angle. And that inscribed angle is equal to half the arc. So if I were to measure this arc in degrees, that angle would be half those degrees. So when you have a quadrilateral that is inscribed in a circle, well, we already know the four angles of a quadrilateral add up to 360, and each of these angles equals half its arc, and all of the arcs add up to the whole circle. So it's a little bit of algebra, but you can show that opposite angles have to be supplementary. And it's an if and only if. So if opposite angles are supplementary, then the quadrilateral can have a circle through all four vertices. We use that in our geometry sometimes when we want to show that a certain 4 points, like I just know these 4 points, let's say, I'd like to show that those 4 points lie on a circle. Well, maybe it's the case that I can prove that the 4 angles, opposite angles being supplementary, can I show that these two angles add up to 180? Is there some special property going on? So that's what a cyclic quadrilateral is like. Let me just show you what I'm talking about in a specific example. I'm going to measure this angle, and it turns out to be, let's get it on the screen nice and clear, that turns out to be 86.2. Now let's measure the angle that's across from it, and we'll get this guy. This guy's going to be 180 minus 86.2. Let's add these two angles. I can do that with the calculator that they give me. I'm going to have this plus this, and it comes out to 180 clean. And here's what's nice about Sketchpad. I can move point A around. It changes some of the angle sizes. But this 180 doesn't change. Even though the angle sizes are changing, these two opposite angles add up to 180. And since all four angles add up to 360, the other two opposite angles have to add up to 180. So if you have opposite angle supplementary, a circle goes through all 4 points of the quadrilateral. That's what cyclic quadrilaterals are like, and that's what they're for. Another thing that I do with circles and segments in circles is, let's just say that I couldn't find this center. Let's say that I have a circle and I don't know where the center is. So what you can do is do the perpendicular bisector of two chords. So here's a chord, construct the midpoint, and then click on that same chord, construct the perpendicular. And this new guy, let me make him a different color. This new red guy is the perpendicular bisector of DC. That's the perpendicular bisector of DC. And it's the case that any perpendicular of a chord, any perpendicular bisector of a chord contains a diameter. So this red part that's in the green circle is a diameter. If I do that again, if I pick another chord and do the construct the midpoint and then construct the perpendicular, I get the center back. Now remember, I hid that center. So I'm going to just show all the hidden, and that center is right where it's supposed to be, right where those two perpendicular bisectors meet. So this is another nifty property. The perpendicular bisector of a chord contains the center. Also, if you have a diameter that's perpendicular to a chord, it bisects the chord. It cuts that chord in half. It also cuts this arc DC in half. So that's called the Sword Theorem in the book, because everything's getting cut in half. So these two properties, we use them a lot in construction. And it's good to know and be able to use these kind of things, especially these two specific topics, cyclic quadrilaterals and the Sword Theorem. All right?